Yes. Perfect. Awesome. All right, welcome to the DESN2000 crash course. You're one of 3 people here. Oh, there's more people coming. Awesome. DESN2000? Yeah. Hell yeah. All right. This will be covering the entire course in terms of theory. We will start off with a course overview. The dinosaur will make a very common appearance throughout the show. If this entire course is about an introduction to embedded systems, and if you look at a week-by-week overview, that's how I've structured the rest of this crash course. So I have gone through and... Why can't the stream see? Oh, what's the stream seeing? Oh, God.
I mean, it has logos and camera, but the display's checked.
Oh, no, it's because PowerPoint does it. Okay. One sec. From beginning. Display settings. Duplicate slideshow. You can see it now? Can you see it now? Yeah. Just oh no, you can see it. Yeah, so I can. Right. We'll see. Oh, does the slides change? Perfect. Okay. Moves. I have structured this crash course where I have gone through several past papers. As I'm sure you know, David does not release past papers, but in like 2011, the previous iteration of this course, they had a series of past papers. I found a 2018 past paper, I found a 2021 past paper. I have gone through and I have absorbed the style of those questions, and I have written down about 3 questions relating to each week of course content. This is a good like sample paper kind of thing, and we will be going through it. The questions are kind of heavily theory focused, that it's more easier to talk about content. And then at the very end, we have a nice final boss question where it's just a big code bash. And fun fact, that's the exam I got in my, that's the question I got in my final. So expect very similar stuff in your exam. Week 1 was a very easy introduction to the course. It was just talking about, if any of you have done Comp 1521, it was basically the exact same thing crash coursed into 1 week. We talk about the ARM as a company, ARM as a processor type, and ARM as the programming language. We talk about the pipeline. We talk about what the assembler does, and we talk about registers, which is how we store information to do our calculations. In week 2 and 3, we talked about ARM assembly specifically. That's the programming language. We looked at data processing instructions, which include arithmetic like add, subtract, multiply, and then logic and shifting, multiplication, and how to do multiplication without the multiply command, because the multiply command is very slow. We talk about memory access, which includes loading, storing, how the types of addressing modes, and then we talk about something called endianness, which we will cover shortly. In week 3 and 4, we talked about control flow, which is how we branch between, which is how we evaluate a condition, and then we decide what we want to do from this point of time. It's called control flow. We talk about jump tables, which is a way to implement a big if statement very fast. Then we talk about functions in week 5 and the stack. In week 7, we talk about I/O, which I'm sure you're all very familiar with in your projects. In week 9 and 10, this stuff is a bit harder to assess in the exam. There will only be a very few kind of surface level understanding questions on the week 9 and 10 content. They include exceptions and about the compiler, and the week 8 content is not particularly assessed. Week 8 was about UART, which is not assessed. Crash course structure, like I said, it's grouped into sections by the week's content that it tests. The questions are inspired by past papers. These are all my inspiration past papers. And the final exam has 100 marks and runs for 90 minutes. The questions I've written, I have put about 120 marks in, so it should take about 2 hours if you do this yourself. All right, right into it. Week 1, the very first thing that we covered in week 1 was the concept of a pipeline. A pipeline is a way that we can optimize the performance of our processor by having it active at all times. If you think of a normal instruction, like the add instruction, right? It has to get the information that it needs. It has to understand what the add instruction is actually saying. Where do I go? I have to go from register 0, R1, R2, etc. It gets the information, decodes it, and then it actually does the task, so it executes. So we have three vaguely discrete stages. We have a fetch stage, a decode stage, and an execute stage. These three stages cannot run at the same time. For an instruction to run, it must go to the fetch stage by itself, and then the decode stage, and then the execute stage. We can speed up the processor by having these things run in parallel. Once one instruction finishes fetching and moves on to the decode stage, we have another instruction start fetching. And you move on, move on. So we have a three-stage pipeline in our processor. This is ARM7 is the architecture of our processor. In ARM9, they have two more stages, which is what most processors nowadays have. We have two extra stages. We have a memory stage and a write-back stage. So that's a 5-stage pipeline. Our processor here only has a 3-stage pipeline. Since each stage uses separate hardware, we can parallelize it. And without a pipeline, we would have to go to these stages one by one. So there is no parallelism, right? So if we have the classic, actually, this is the classic diagram. We have a clock cycle 1, 2, and 3, and then over here, can we zoom? We can't. We are fetching, this is instruction 1, decode, and execute. God, this sucks. Fetch, decode, execute. Fetch, decode, execute. This is the same diagram that they use in the lecture slides. And this is instruction number 1, instruction number 2. As you can see here, the top axis is our number of clock cycles. Running 2 instructions takes 4 clock cycles now. In the first clock cycle, we fetch the first one. Here we decode and fetch. Here we execute and decode. In the final one, we execute the last instruction. 2 instructions took us 4 clock cycles. If we didn't have the pipeline, we would have to go fetch, decode, execute, and then the next instruction goes here, right? So it costs us 6 clock cycles. So in general, the speed up, we'll say, of having a pipeline of 3 stages is that as you have more instructions, we have a 3 times speed up in the performance of our processor. Now, if we look at we'll say back to the execute stage, right? We say that the instruction here, on average, once we keep adding more instructions, each instruction takes 1 clock cycle to execute. Add or logical shift, they take 1 clock cycle. But our branch instruction takes longer than that to execute. Any ideas why? Perfect. So when we move on to this instruction here, the execute relocates our program counter. Our program counter keeps track of where we are in our program, right? So the branch moves off to somewhere else. However, the pipeline has fetched the next sequential instruction, right? This instruction here could be branch to instruction number 7. However, we have fetched instruction number 2, and we've decoded instruction number 2. This is bad, because we need to clear the pipeline, right? It's gone and fetched the wrong thing. If it continues executing instruction number 2, that's bad. We need to jump to instruction number 7. So this is called a pipeline flush. We have to flush the pipeline, clear everything it has, and then restart. So therefore, we have a fetch, decode, execute, and here in the next clock cycle is when we start fetching again. So we have lost 2 clock cycles of speed, which is why a branch instruction is said to take, in quotation marks, 3 clock cycles, whereas an arithmetic instruction takes only 1 each. All right. Next up is a very standard question. You will almost certainly get this kind of calculation in the exam as a throwaway 1 or 2 marker. all of you have done Elect 2141, so you should be reasonably familiar with the concept of these. I will run through it very, very quickly. All right, the question was express 43.21 from base 5 into base 9. So the first thing we do is we don't actually know how to work with base 5 or base 9. So we convert it to base 10 because we're lazy. In base 10, we represent, as you know, this is the 5's place, this is the 1's place, this is the 1/5, and then this is the, sorry, give me a second. And then this is the 25th place. So we have this 43.21 is equivalent to 4 times 5 plus 3 times 1, and that becomes 23. Then we have 0.21, which is, this is a 5th, and then this is a 25th. So there's 2 fifths plus 1 25th, and that is 0.44. So now we know that 43.21 in base 5 is 0.44 in base 10, sorry, is 23.44 in base 10, and now we can convert this into base 9 as required. The rigorous way of doing this would be divide by 9, divide by 9. However, you can see that 23 is 18 plus 5, which is 2 9s and a 5, so it's 25 in base 9. And then 0.44, we have to go the long way around, which is repeated multiplication. What we do is we multiply our decimal by the base we're working with. So 0.44 times 9 is 3.6. What's the full one? 3.96. So we keep the 3, and then 3 is our next decimal point. Let me get a calculator up here, sorry. So here, 0.44 times 9, we get 3.96. So 3 is our next decimal place. And then we take this fractional bit and we multiply it again. So you get 0.96 times 9. 0.96 times 9 is 8.64. So we take the 8, put it as our decimal, and then keep the fractional bit, multiply again. 0.64 times 9, 0.64 times 9 is 5.76. So we take the 5, go in here, and you could keep going to more accuracy if you want. This should be more than enough, which means that our final answer is 25.385 in base 9. Mm-hmm. How many decimals do you reckon we should go to? Same as they provide. They will tell us. As in, if they've given a 2 decimal place number, you just go back with 3 decimal places. There is a good chance that if they can also ask you to express this in binary, or they could say express it as a word, which is 16 bits, in which case they will tell you how many bits for the number and how many bits for the fraction, and you would allocate accordingly. So it's common to be like, use 8 bits for the number, and use 8 bits for the fraction. Mm-hmm. Word is 32 bits, my bad. A word is 4 bytes. However, on a technicality, as in the course, we do say a word is 4 bytes. However, the ARM processor manual says a word is 2 bytes. That's separate. As in the course, 4 bytes. 4 bytes. Cool. Next up, week 2 content. It says, write an ARM assembly language code to compute 1000x minus 13y without using the multiply instruction, and count how many clock cycles your code takes. Assume x and y are available in registers R1 and R2. So we have 1000x minus 13y. 1000x minus 13y. I might actually get the document camera up and just do it by hand, might be easier. Give me a second. There we go. Cool. So it was, can the camera see? Yes, it can. Is there an option where we can, no, that doesn't, can you all see that clearly enough? 1000x plus 13y? No, you can't. There's a preview mode somewhere.
There's a preview. Try and find it.
There we go. Ooh. Focus. There we go. That'll do. 1000x plus 13y. So you can use the multiply instruction to do this in a very one-shot way. However, the multiply instruction depends on how the processor has been made. It can sometimes just be a very repeated addition again and again and again and again and again. So if you're timesing by 1,000, it would take you 1,000 clock cycles. So this is obviously suboptimal. So we can rewrite this in terms of shifting and adding. So our processor works in base 2, right? So we can easily multiply a number by 2 by just shifting it by one place to the left. If I have, for example, the number 110, which is 5, if I want to multiply this by 2, I just shift it one to the left. So I get 1100, and as you can see, this is this 5? 2, 4, no, this is 6. And then this is 8420, so 8421, this is 12, right? 6. So to multiply a number by 2, we just shift it one to the left. So we can do 1,000 in the same way. You can't, 1,000 isn't a power of 2, right? Multiplying by 2 squared, you shift it 2 bits to the left. So to do 1,000, you have to break it up in terms of additions of powers of 2. The closest power of 2 to 1,000 is 1,024. So we can say 1,000 is equal to 1024 minus 24, right? Oh, perfect. 1,000 is 1024 minus 24. This is, 1024 is 2 to the power of 10. 24 is not a power of 2 either. So we can split 24 up further. We can say that 24 is 16 plus 8, right? And 16 is 2 to the 4, and 8 is 2 to the 3. So we get 2 to the 10 minus 2 to the 4 minus 2 to the 3. Does that make sense? So that is how you can represent 1,000 in terms of additions purely in powers of 2. And then similarly with 13, 13 is 8 plus 4 plus 1, right? And that is 2 to the 3 plus 2 to the 2 plus 1. And then, so this is 1,000. Therefore, if I move this all the way up, is that on screen? Yes, it is. Beautiful. So we can go through, so this is, therefore, 1,000x is 2 to the 10x minus 2 to the 4x minus 2 to the 3x. So that would be a very conceptually, you would be doing x, shifting it left by 10, then you subtract x, shifted left by 4, then you subtract x, shifted left by 3. Right? If we write this out in code, turn off the document camera, move back to good old program here. We said that 1,000 is 2 to the power of 10 plus 2 to the power of 4, minus 2 to the power of 4 plus 2 to the power of minus or plus? Minus 2 to the power of 3. So we could say that we want to shift. So we want to shift left. LSL is logical shift left. We want to shift left. We have, what register was it saved into? We have R1 has X and R2 has Y, right? Okay, we want to take the R1 value, shift it left by 10, and store it into some temporary register. Let's say R3, because R2 is already taken. So we save into R3, we take R1, and we shift it left by 10, right? And then we can also, we need 2 to the power of 4, so we can do LSL R4, take the R1 value, shift it left by 4. And we want to subtract. We can subtract R3, or save, so what the destination register, and then A and B, right? So we can save it back to R3, doesn't hurt. We can take the R3 value, subtract by the R4 value. And this, so let's just add, it's good to add comments to just describe what you're doing. So we can say R3 is 2 to the power of 10x, R4 equals 2 to the power of 4x, and then R3 equals 2 to the power of 10x minus 2 to the power of 4x. And then we also want to subtract 2 to the 3. So we can do subtract R3. So you could do a copy of this, right? Instead, just do it by 3. And then you could say R3 is 2 to the 3x, right? You could shift it again. Alternatively, ARM assembly offers you a way to do shifts in an instruction itself. So the immediate value you can replace with a shift operand, as they call it. So what you can do instead is you can subtract, save into R3 again, take the R3 value and subtract it by R1 LSL by 3. Right? And what this does is it takes R3 equals all of that minus 2 to the power of 3x. Mm-hmm.
Is that one? Oh, sorry.
This one? Yes, it is. Yes, it is correctly more efficient. So if you do it as a separate instruction, it's a whole instruction, it saves it back. Mm-hmm. Question? Oh, yeah. However, if you do it integrated here, what it does is it takes the immediate value. If you remember the data path stuff from 2141, you might not. Instead of taking an immediate value, it sends the immediate through a shifter, and a shifting by a constant value is immediate. It doesn't take like any clock cycles to do. It's just like a remapping of wires, so to speak. So you can do this very fast.
But for line 6, that's still one clock cycle.
So because you have to write back to a register.
Okay.
So in line 6, you're writing back to R3, so that costs you a clock cycle. Yeah, like the whole thing costs you a clock cycle. Here, what you're writing back is this final instruction here, like is this final value here. So this entire thing only takes that one clock cycle. Cool, cool. You question? Yeah.
I was just wondering, for this one, we chose to do 2 to the power of 10 minus 2 to the power of 4 minus 2 to the power of 3. Why did we choose that over like 2 to the power of 9 plus blah, 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 blah?
Let's try it.
Easier?
Let's try it. 1,000 is 512 plus, well, we'll go bit by bit, right? 512 plus 256, where does that take us?
2 to the 9 plus 2 to the 8 plus 2 to the 7 plus 2 to the 6 plus 2 to the 5 plus 2 to the 3. So it's a lot.
It's a lot. So there is your reason, right?
So we just choose it, like whichever one's easiest?
Yeah. If they ask you to write the most efficient code, then you would have to go this way.
Okay.
However, if the idea of subtraction hurts, then you can just go up and up and up.
Yeah.
The benefit of using your way is easier because you can just convert to binary. Like take the 1,000 value, convert it to binary, and that tells you how many stuff to add, right? Because each bit represents a place value. This way, there is no easy way to do it other than just like look at the number and be like, well, the closest power of 2 is 1,024. So that is the method. Question? Cool, cool. You could do the same thing for the 13x. I'm not really bothered. So let's just pretend that R3 has 1,000x. So this is now 1,000x. And then let's pretend that R4 now has 13y. We just do a simple subtract, save it into R0, let's say R3, R4. Right? This is the end of our task. Cool, cool. It has, this is going to be a pain. Display settings, duplicate. There you go. Auto, please let me know if it disappears from the screen again. What happened? All good? Mm-hmm. Yes. Perfect. So in this case, all of our instructions are just arithmetic instructions. So you just, if you want to count how many clock cycles your code takes, you just count the number of instructions. However, what's the caveat? So do we say that, all right, let's pretend this is all our code, right? We have 5 instructions. All right, our code takes 5 clock cycles. Plus 2, why plus 2? Sure, or the first one takes 3. So when we set up the processor, right, we can't fetch all 3 instructions in one go. We have to fetch the first instruction, and then we fetch and then in the next clock cycle we decode that, and the next clock cycle we execute that, and every subsequent instruction takes that many clock cycles. If I draw this out real quick, we have 1, 2, 3, 4, 5 instructions. We have 10, right? So this is our, this axis is our, horizontal axis is our number of clock cycles, and then this is the instruction. So we fetch the first one, decode, execute, then we fetch, decode, execute, then we fetch, decode, execute, right? There we go. So you'll see that 5 instructions take 7 clock cycles to finish running. 5 instructions take 7 clock cycles to finish running, because you only start executing after the first 2 instructions to set up the pipeline. So a good rule of thumb is the number of data processing instructions you have plus 2. If you have a branch, then add 2 more. Cool. Next up, if the word 0xCAFBT9A is stored in memory, starting at address 4000 in Little Endian convention, draw a memory map to show how the content is stored. That's a lot of words. Does anyone know what Little Endian convention is? Mm-hmm.
Just a guess. If it was in an exam, I'll assume Little Endian means the most significant bit is on the left, right, one of those.
Maybe. Potentially. The way I remember it is the end of the word is stored at the little address, right? Hence the name. Little Endian, the end of the word is stored at the little address. So this is a kind of unintuitive way of storing content. But the way this would be is that, like we said, the end of the word is our 9A, right? Like the end byte. 9A is stored at the little address, which is 4000. So that means we would go 9A, H, E, F, B, C, A, right? Because we partition this up into bytes. Each address stores 1 byte of memory, and a byte is 8 bits, and each hex value is 4 bits, so we partition that up, and we go, the little address, which is 4000, holds the end of our word. So this is how we store it. In big endian, we would erase that, and the big address stores the end of our word, and that is a more intuitive top-down approach, right? So we would just go C, A, F, B, H, E, 9A, right? If it was big endian, big endian. The big address stores the end of our word, so it would be this way. Little endian is this way. So now that we have stored our stuff in little endian, if we erase all of that, if we read the information in a big endian convention, big endian assumes that the big address stores the end of our data, right? So that means reading in big endian format would read this upside down. So big endian reading would read this as 9A, 8E, FB, CA, top down. However, in little endian, we store it backwards. So this is not really an issue for us because our processor is like hard-coded to store information in little endian convention. Just pick a convention. However, if you are, let's say, interfacing between two different processors which operate on different conventions, you need to keep that in mind. So if we read it in big endian, we get 9A, 8E, FB, CA. So you just invert all the bytes from order. Cool. Next up, big loaded question. Explain the difference between pre-indexed with write back, and post-indexed addressing modes in ARM. That's a mouthful. Before we go ahead, I want to introduce you all to your formula sheet from in your exam. This is the practice exam that David releases on Moodle. You may or may not have seen it. Heads up, it is not a full-length exam. It's also significantly easier than the actual final exam. But however, at the end, you get access to these data sheets. These data sheets are very important. It's extremely worth your time to kind of just know what information is stored on the data sheets so that you don't have to like memorize it, right? So the question yapped about some pre-index and post-index thing. If we look at our data sheet, wow, pre-index and post-index is on here. This data sheet tells you the syntax for how to write a pre-index instruction, how to write a post-index instruction. There's a whole bunch of square brackets and exclamation marks, etc., etc. We'll cover that shortly. But yes, it's very useful to know. Like I said, we used the LSL instruction, right, which is logical shift left. They have it here. There we go. Logical shift left by an immediate value. There's also logical shift right, arithmetic shift right, and then rotate right. This might come up later. I'll explain it then. But back to pre-indexed and post-indexed addressing, right? So the difference between pre-indexed with write back, and post-indexed. Judging by the name, pre-indexed, we have a register with the address of our information, right? We want to give it an offset specified by RM, right? Or over here, by an immediate value. We have a value and then an offset. So when we read this kind of information, it's very useful if you have, let's say, a array, right? The array has 1, 2, 3, 4, 5, 6, 7, right? When we store arrays in memory, if you remember from 1511, what we actually do is we store the address of the first element in the array. We don't actually store the entire array as a variable. So if we do like int x, I think that's the syntax, right? What x actually is x is the address of the first element of the array. If you want to access the second element of the array, we do x1, right? We can do like x0, x1. What this is actually doing is it is taking the address, which is x, and then it's adding 1. So this is original address is x, right? If we want to get x1, we take the address of x, and then we add 1 byte to it. We add 1 byte to it, and then we can access the memory at that index. If we want the fifth element, or I should not use 5 here. Let's use 10, 20, 30, 40, 50, 60, right? If we want the fifth item in this array, we add 5 to the base address. So that would offset us 5 bytes to the right, which is our fifth element in the array. So our ARM assembly has a way of doing this, which you provide the base address in Rn, and then you provide an offset in Rm. You can also scale that offset, as is classic in ARM. You can left shift it, you can right shift it, you can rotate it, etc., etc. So now we get into pre-indexed and post-indexed. In pre-indexed, question?
For that integer array, would you have to scale the index by 4? It's 4 bytes. So if you want to get to like the first thing you do 4 times 1,
You're right.
like
Yes.
if it was
If it was
the char,
a character array, you don't need to bother. In integer arrays, like was just pointed out, an integer is 4 bytes. So we want to access the fifth element because these are 4 bytes each. So this is actually an offset of 20, of 5 times 4, right? Because this is worth 4 bytes. The next one is worth 4 bytes. The next one is worth another 4 bytes. So that is where your left shift is very useful, because you can take the base address, you can take your index, and then you can shift it by 2, which is multiplying by 4. Therefore, you can directly access the multiple of 4 that you need. So now we have pre-indexed, post-indexed. In pre-indexed, we say that the base address plus the offset is calculated before accessing the memory, right? So it takes the base address, it takes the offset, computes it, and then it goes and accesses that point in memory. In pre-indexed with write back, it stores this value back to your register. So we said that we access it from, a register contains a value, and then the offset, and then we add them together, we go access that address. If you're accessing an array, you don't want to modify the base address of your array. You want to actually remember it so that you can access any random offset. However, in pre-index with write back, it writes back the value to that to the original register. So if you access, keep this. So in normal pre-indexed, the syntax here was, there we go, we'll do this way, right? And copy that. This is the syntax. LDR, we give it a destination register, let's say R0. This is R4, let's say. R4 contains, so this is our destination register. We want to save it, what way we want to save the value into. R4 contains the address of our array, and then let's say this is number 6. We want to access the 6th element of our array. This will do it normally. You'll notice that in the formula sheet, there's a exclamation mark in brackets. The exclamation mark is the write back command. So if we put an exclamation mark at the end, what it does is it tells the processor, once I get the 6th element of the array, update R4 to be that address as well. So what this does is basically 2 commands. This accesses the previous, and then it adds R4 with 6. So it updates the register. This is good if you are never going to go back to any random address in your array, and you want to just like step through one by one, operate on it. Therefore, you can use that. This is like a linked list, if you will. Right? This is the, so this is our pre-indexed. This is our pre-indexed with write back, which basically does this as well. And then we have post-indexed. As you can assume by the name, post-index accesses the information and then updates the address register. So the syntax for this, syntax here, kind of makes sense, right? The square brackets signify an address or signify that you're addressing something. However, in post-indexed, all the like offset information is post the addressing. So what this does is it gets the information at that address, and then it adds 12. Do you think post-indexed has write back or has no write back? Write back? Why so? Just cause. Fair enough. So we say that pre-indexing we have two methods. We can either access the element with an offset and not write it back, or yes, write it back. With post-indexed, if we access the element and then apply the offset, if you don't write it back, you're never using the offset, right? If you access it, if you have the information, you get the information in Rn, and then there's an immediate offset hanging off the edge, you must write it back for it to actually be useful, so that the next time you access the information, it's already been updated. The address has already been updated. If you don't add the write back, it makes no sense to have post-indexing at all. Cool? So that is a quick summary on pre-post. Did we cover all of it? Yes. Example instruction, as you saw, the datasheet has all that. A use case, well, the first one is good if you want to keep the starting address of your array and then move on. And the other two are good if you are never going to go back to arbitrary elements. You're just going through a whole set of data. You're going to go from start to finish and never again. Branching. The B and BL instructions do not allow branching to a memory location beyond 32 megabytes away. Why? Fun fact. This is another case of the datasheet comes in. This here is the format of our instructions, right? So an instruction is really just another series of zeros and ones stored in memory that our processor just goes through one by one, reads, understands, and runs the instruction, which is why you have a fetch stage in our pipeline. We have to get the next instruction from memory and then decode it and then execute it. If we look at the format of our branch and branch with a link, we see that we have the condition field. You know, you have like branch of equal, branch of less than, etc. We have a 101 for some reason. We have a link bit, which is set 0 if it's just branch and 1 if it's branch with link. Then we have an offset. As you can see here, the offset goes from 0 to 23 bytes. Therefore, we can assume that there's 24 bits available, so we can do 2 to the 24 bytes. There we go. That's just 16. The question said that it allows branching to up to 32 megabytes away. Any idea how this is overcome? So the format here says we have 24 bits for the offset. If we do 2 to 24, put that in bytes, we get 16 megabytes. However, it says 32, not 16.
No, just had a wild guess. Is it because the pointer is always like 2 bytes below?
So that would be, well, that would be plus 2 bytes? Well, is it plus 2 bytes? So to the 24 minus 1, 25 minus 1? 2 to the, where do you get 25 from? Well, because there's 0 to 23, so we have 24 bits available. It's 0 to 23.
Is it the size of every address?
Yes. Yes. So an instruction is 32 bits, right? Which is 4 bytes. So there is really no use in being able to address to at a resolution of 1 byte. We address to a resolution of 4 bytes instead, so that you don't go like halfway through an instruction. If you have like an offset of 1, if you start at like 0, offset of 1, that means you'll end up like halfway through the instruction. You always want to go to the end of the instruction, right? So this offset field contains the offset in terms of 4 bytes, or in terms of words. With that new knowledge in mind, if we do 2 to the power of 24 times 4 bytes, we get 67 megabytes. Yes. So if you remember signed and unsigned numbers, the very top bit is reserved for our sign, our plus minus, right? And then our remaining bits are used for the actual number. So therefore, we have 23 bits available for the address, and then the last bit is for the sign. So finally, we get 2 to the power of 23 times 4 bytes, and we get, well, there we go. No, there you go, 32. You'll see that this says 33.55. That's because if we do 2 times 4, 33.55 in terms of just like power of 10. However, in power of 2, this is exactly 32 megabytes. So that's a fun piece of trivia. Next up, given R0 is some arbitrary value and R1 is another value, consider this instruction. What are the values of the NZCV condition flags after the instruction, and which of the branches will be executed? What are the NZCV flags? Any ideas? Perfect. When we perform an instruction, it will set these 4 flags in our processor. It sets a negative flag, which tells you if your result was negative. It sets a 0 flag, a carry flag, and an overflow flag. Overflow, V for overflow. If we have an instruction, let's say add or subtract, let's say subtract 1 minus 4, that would set the negative flag, right? Because our result is minus 3, so the negative flag is set true. If we have an instruction called TST, I don't know what that does. Where do I go? Datasheet. If we go here, we look for a TST instruction, you'll find out that it is right here. Bitwise test. The TST instruction takes a register, and what it does is it updates the CPSR flags for RN ANDed with shift op. Shift op is just a fancy way of saying a register or a register with shift. Right, so we know that the test instruction is basically the AND instruction, except it updates these flags. A normal instruction like AND does not update these flags. A normal subtract instruction does not update these flags. You must tell the processor specifically to go and update these flags. We do that, which is why you see a S in a curly brackets here, right? So if you have a normal add instruction, this just adds and keeps going. If you say add S, what this does is it does the add, and it also updates these status flags. Question?
Does that take off clock cycles?
No, it does not. It's automatic. So the way you compute the negative flag is you just look at the sign bit. The way you compute the 0 flag is just AND all the bits together. The way you compute the carry flag, I think it's, there's something funny, I forget. An overflow is if something flew off the edge. So adding an S does not add an extra computational time. So the TST instruction, it updates the CPSR flags for RN and shift op. But we also have an AND, normal AND instruction, right? We have a normal AND instruction. So can anyone think of a use case that distinguishes AND S from the TST instruction? Let's say, versus TST. Well. Mm-hmm. What do you mean, or? What do you mean?
Well, I don't know which one.
Okay, fair enough. Well, it doesn't do with storing back. The syntax for the AND instruction, you'll see that it has a destination register, and then your number, and then your shift op. However, the TST instruction does not have a destination, right? The destination is the flags directly. So the TST instruction saves you having to actually modify register's value to get those flags in. So that's when you would do that. You'll also, if you look at the compare instruction, it just does a subtraction. and the command instruction just doesn't add, right? So these four are the same as add, sub, and XOR, just without writing back to register. So what was the question? That? Can I copy from here? No, I can't. Cancel. 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 All right. Right. I have R0 is this and R1 is this. Right. The TST instruction, what it does is it basically does an AND between these two values. However, the question also specified ASR1. Anyone know what an ASR means? No? Yes? What does arithmetic shift mean? So we have LSL or LSR, which is logical shift right. Then we have ASR, which is arithmetic shift right. What's the difference? Perfect. So if we a new file, we have a, let's say we have a number, some random number, right? This is a negative number because we have a 1 at the start. If we have another, that's not a binary number. We have another number. This is just a normal number. It's a positive number because there's a 0 at the start. So what an arithmetic shift does is if I take this value and I shift it right, shifting just adds zeros to the front, right? However, I have changed the positiveness of our value. My negative number has suddenly become positive. That's bad. So that's a logical shift. A logical shift just chucks zeros onto one of the ends. An arithmetic shift looks at the first bit and fills in by that bit. So if I arithmetic shift a negative number, it just chucks on ones. If I arithmetic shift a positive number, it chucks on zeros at the start. Mm-hmm.
That still make it still divide by 2?
Yes. Yes.
Even for a negative number.
Yes.
So it was like negative 32 go to negative 16.
Yes. Oh.
Getting used to
Oh.
shift, right? It go to
Yeah, it would.
It would be negative 32, then it would go to positive 16.
Yeah. Which is, I don't even think it'd go to positive 16.
No, it might just do something weird.
It would mess with the 2's complementness
Right.
because your bit is just in a weird place. So if you're dealing with negative numbers, you should use arithmetic shift right. Any idea why there's no arithmetic shift left? We have logical shift left, logical shift right. But where's arithmetic shift left? Yeah, exactly. You're shifting left. So there's not much you can do with the sign. Simple as that. Rightio. So we have these values. We want to take this one, shift it right by 1, and then AND them together. Does everyone know the calculator hack to converting hex to binary? You can do that in your calculator in just one shot. If you have the FX100, you have your FX100, right? If you go to mode and you go to base N, base 4, there we go. Now you can set this to hex. You're in hex, and now I can give DB97530F. I can hit the equal sign, then I can hit binary. You can see bin up here. If I hit binary, that's too big of a number, unfortunately. But if I just convert, let's say, DB97, syntax error. To go back to hex mode, there you go. If I save that and I go to binary, it's still too big. What's the limit it can do? Right. D97. There we go. You can convert between hex and binary. There seems to be some limit in the length of your number. I was not aware of that. But yeah, you can convert between hex and binary. Using that, I can trust that you can do this conversion. I cannot be bothered right now, so I'm just going to ask good old Google. There we go. That's a big number. So DB97 is equal to that in binary, and then all that. Whoop. That, right? Missing 3 zeros at the start because 1 is it's done funny conversion stuff. There we go. This is our conversion. We convert the hex to binary. Now our job is to the test instruction, right? We have TST R0 R1. What it does is it ANDs these two together, except it shifts R1 1 to the right. We can do this shift. We see that there's a 1 at the start, so we chuck a 1 on that end, and we discard that last bit. Let me not discard it. I'll throw it off to the end for good reason. Now while we just AND these together, you'll see that, oh wow, this has been rigged very perfectly, that no 2 bits are 1 at the same time, right? The AND of this is exactly 0. Our final answer is AND is 0, right? So now if we look at our NZCV flags, our result was 0, right? Is 0 negative? No. Is 0 0? Yes. Carry. What does carry mean for an AND instruction? Not much. However, for a shifting operation, the carry bit contains valuable information. The carry flag in a shift contains the last number that fell off the edge in any direction. If you shift to the left, the carry flag will contain the very last bit that fell off the edge. If you shift to the right, you'll see, that's why I saved a little 1 here. The last bit to fall off the edge was a 1, so our carry bit is set to 1. Overflow flag truly has no meaning, so we can just put like an X, or like we don't know what it does. Right, so we have N is 0, Z is 1, C is 1, and V is question mark. Part 2 of the question was which of these 4 branches will be executed? How am I meant to memorize what bacon, lettuce, tomato, and beans is a conditional branch? You don't. Again, you look at your good old data sheet. Down here, you get information about the conditional fields. We had to deal with these 4 instructions, right? BHS, HS is over here. HS is checks if a number is higher or same, and it checks whether C is set. Was C set? Yes. So therefore, BHS will execute. BLO, is C clear? No, it will not execute. BLT, LT, checks if N is not equal to V. In our case, we don't know what V was, so the answer is question mark. Like, you have to say in the exam, if they ask this, it is unpredictable. We cannot say whether BLT will execute or not. And then BPL checks if N is clear, N is 0, so N is clear, so BPL does execute. So that is our final answer. Cool. Next up, explain the basic operation of a jump table. Why may this be preferable to case-by-case compare statements? And then implement the below switch statement in ARM assembly using a jump table. Hence or otherwise, give the disadvantages of a jump table. So this is basically what are the good and bad things of a jump table, and write me a jump table. You can see here that we have a switch statement. It switches on some kind of code, and if the code is 1, then it adds. If the code is 4, then it subtracts. If the code is 5, then it ANDs, 7 it ORs, otherwise it turns a negative. So if I was to do this, do I have this code? No, I can't copy that out, unfortunate. Let me just write this down real quick. Switch on opcode, right? We have case 1, x plus y. case 2x minus y, case, this was actually 4, 5, x and y, case 7, x or y, and then default minus x. Right? So we have this. If we were to convert this into standard ARM, oh, that's ugly. Rip. All right, convert this to ARM. We would firstly compare opcode with 1, like whatever register opcode is, and then branch if equal to wherever the case resides, right? And then we have compare opcode, branch if equal somewhere. Compare opcode with 4, and then branch if equal somewhere else, right? As you can see, if we had like case number 7, 7 is all the way down the bottom. So if we have our first comparison and it matches, then it only takes like these 2 clock cycles to run. However, if we match case number 7, we end up taking like 8, 10 clock cycles by the time we reach that stage. So that is not particularly good. Enter jump tables. What a jump table does is it's basically, so you saw how we had like a branch of equal and another branch of equal. A jump table is basically an array of all the places where to jump. So if it's 1, we jump to somewhere, right? If it's 2, we jump to default. If it's 3, we jump to default. If it's 4, we jump to somewhere else. If it's 5, it's, I don't know, 5, something else. And then 6, it's default. And then 7, it's something else. And then 8 is our default, right? So a jump table is basically an array of all the addresses. And then what you can do is you can just take this array, find this case, get that address, and jump straight there. So what it would do is it would do an LDR instruction with like LDR using opcode, let's say R0, using opcode and then array as an offset, right? It uses the array and the opcode as an offset, sorry. Stores that into R0, and then what you can do is you can just, can you do this? For branching, you actually have to update the program counter directly because our branch instruction cannot take registers. Our branch instruction takes a label, or it takes the direct address. It can't go to register and then take the address. So what you have to do instead is, instead of loading it into like R0 and then branching somehow, you just load it directly into program counter, like that. It's a bit goofy, but that's how you do it. So you can load into program counter array or opcode, and then, as was pointed out earlier, this is an array of addresses, and our addresses are 4 bytes long, so you would shift the opcode by 2, right? So this is kind of the pseudocode as to how our jump table works. In ARM, the way we declare an array is using the DCD command. So you would DCD somewhere, and then DCD that, and we would, not bad, DCD. DCD stands for, I think, declare double word, and it just writes this address into memory, and then we would give it, so instead of array, let's say jump table. We would declare our jump table as a label. This would take the value, it would take the opcode, shift it by 2, get that index of our jump table, and then load it straight to our PC. Right? And then, your question?
When we had multiple instructions in one case, did we, how big did that block? Because they're all stored contiguously, aren't they?
So the jump table contains the address of case 1. And then we would have our case 1 label here where we can do how many ever instructions we want, right? And then case 2 is another address, and it has a whole bunch of other instructions. So address case 2, right? So it doesn't actually matter how many instructions you have per case, because you're storing the address to where that case starts. You just jump straight there. So if we're talking in ARM, we would just do exactly this: DCD case 1, DCD case 2, where case 1 and case 2 are our labels. Jump table, jump table is not a register value, so you'd have to actually, the program counter would be at your jump table if you add another instruction here. You know how the program counter is 2 ahead? If you add a little knob here, that means your program counter is exactly at your jump table right now. Yeah, so that would be an extra instruction though, and I'm efficiency, right? So you could just do like LDR R0, the address of jump table, right? And then here you could R0. Alternatively, adding the NOP also costs an extra instruction. However, the bonus of having our NOP here is we can just replace it with our default case. Instead of having a DCD default down here, you could just have a B default, and you could compare here. Compare our opcode with 7. LDR if less than or equal to, what's the condition for that? Less than or equal to is LE. If it's less than or equal to 7, then load this, and then jump straight there. Otherwise, unconditional branch to default, right? The other way of doing this would be taking the value of opcode, comparing it. If it's greater than, set it to 8, and then your 8th instruction here would be your default. Your 8th address here would be your default address. That is one way. This is more efficient. So this is basically all there is to writing our jump table. Question?
Just double checking, we're shifting it by 2 to the left to get the power of 4?
Multiple of 4. Because a DCD stands for double word, which is why I said it's funny how ARM works. But it's 4 bytes. All of our instructions are 4 bytes, where addresses are 4 bytes. So you want to get the 5th element in the array, but the 5th element is, so this is 4 bytes in itself, the next one's 4 bytes, 4, 4, 4, 4. So the 5th element is 20 bytes away. So we take the opcode, times it by 4, which is conveniently a left shift of 2. Cases, this would just have like an add R1, and then case 4 would have something else. Right, so case 1, this would be a default, 3 would be a default, this would be case 4, case 5, default, case 7. We would declare our cases. We wouldn't have a case 2, we'd have a case 4, and then we'd have a default case here, etc. Make sense? Awesome. Can anyone think of, just looking at this jump table right now, what might be the downsides of this? Can anyone now see what the downside might be? Yeah, your jump table needs to be as big as your biggest case. See, if I had 87 cases, I must now have, sorry?
What if your opcode goes past your last case and it wants to default, but there's not that element in the jump case?
Which is why we compare it with the max value here. No, max value here. So we would do a compare 87 first, and then we would jump. And so if we had 87 cases, we now have to go all the way. There you go. I think that's correct. And then 87th case, we would DCD case 87. right? This is an absolute waste of memory. That's a lot of default jumps. So if your cases are very sparse, then using a jump table is kind of bad. Question? That would be very concerning, yes. As in, we said earlier that we have 2 to the power of 23 instructions that we can jump. So if you had more than 8 million possible cases, then you have an issue, yes. Cool, so that's flaws of a jump table. However, if we don't have all of that nonsense, right? If we don't have case 87, in this case, a jump table is potentially good. So it's a trade-off between the time it takes to execute and the store space you have available. If you want your thing to be like infinitely fast and you have unlimited storage, then go for 87 defaults. That's up to you. However, we are working with embedded systems. We're trying to like minimize space and time, so we probably wouldn't use it in that case. Cool. Duplicate. Cool. Next up, more efficiency stuff. Express the below C code in ARM with identical execution time regardless of branch. This question is heavily inspired by one that came in my final exam. You can see here that if button did the else, you would have to run through all these cases and then execute, right? So that costs extra time. So it changes the amount of time it takes depending on where your case was. So our job here is to express this code with identical execution time regardless of branch. Now this requires a bit of creative thinking here, but you can see that button is just a number as a string. So if you remember your, I think A2I in lab 2 was converting strings into numbers, taking like a string number and converting that into its actual number value. So we could do that and then implement a jump table, right? So we could just rewrite this as converting the character to its number value. So we subtract by, I think like 20 or something. You can also just subtract by the actual number. So we would do subtract, let's say assumptions first. The question said R0 is button, R1 is X, R2 is Y, right? So we can do subtract. Let's save into R3. We take the button value, which is R0, and then we subtract the string 1 from it. So that means, comment, R0 would now be 0 if button is 1. Rewriting it better, R0 is the number value of button, subtract 1. If you want to get the exact number value, we can do subtract this. So now the string 1 minus the string 1 is just 0. Or the string 0, we don't have a 0, which is why I used 1. If we have the string 3 minus the string 1, the difference of them is 2, so we save that. Over here, if we have string 0, we can do that. The difference is 3. So the number value is 3. Now, we can just do a normal jump table, right? We declare our jump table. We have DCD. This would be the else case. This would be the case 1, DCD case 2, DCD case 3. Right, so 0, I guess, is the else, and then there's 1, 2, and 3. And then here we would do the same syntax, which is like the same LDR, etc., and then an unconditional jump, be else. So you could do this and then have branches for every case, and that would work. However, if you take a look at the question, as a fun trivia fact, like if you did this solution, this would work. This would be fine. You would probably get the marks, unless they said most efficient code. A more efficient piece of code, if you look, the result value, x and y are the exact same, and x is basically a 1 shifted left by the number minus 1, right? If it's 1, then the 1 is in the 1's place. If it's 2, then you shift it, it's in the 2nd place. If it's 3, it's in the 3rd place. If it's 4, it's in the 4th place, right? So as a kind of high-level overview, we want to take the string value, get it, so take the string value, which is, for example, 1, convert to number, so we have 1, subtract 1, so we have 0, and then our result x is the literal 1 shifted left by number, right? So if we have, for example, string 3, we have string 3 here, we convert to number, we have 3, we subtract 1, we have 2, we shift this left by 2, and we get 0x 0, 1, 0, 0, which is as required. Question?
So we can change the logical flow of the program as long as we say it has the same effect.
Yeah. So 2. So you could express this in ARM. Yes. I think I might have a solution here. Sample solution. Right here. This is my sample solution. Right? So R3 would contain the number of shifts. So we take our thing, we subtract the string 1, then we compare it. This is our else case. You can read this code later. I'll publish the code later so you can take a good look. It is a bit mind-boggling. And then we just shift it by the index times 4 because we're in hex actually. Cool. I might take this one's from the 2011 final exam. This is a hard task. I will not go through this. We will take a short break of about 10 minutes. You're welcome to read this, try and understand it, guess what it does, and then I will very briefly confirm if you have the right answer in 10 minutes. Question?
I was just wondering, for the past paper that we received, do you know whether solutions
No.
were released?
No solutions. Unfortunately, no solutions. No. Short break of 10 minutes. We are back. We are live again. Are we live? We're live. Alright. The quick bit of trivia that I showed before I paused the stream was this random piece of C code. Did anyone in person have a guess as to what it does? Anyone actually bother taking a look? Nope, no worries. So, I'm not going to spoil it. I recommend you like go home and like read it or something. But the steps I would do to understand such kind of thing is try and rewrite this in some form of like code resembling way. Like just give names to all your variables. Just like declare it. Like if you see an LDR, write that as an array addressing. Write them out as storing. Write them out as if statements, etc., etc. And then using this pseudocode, you can convert it into like real code. And fun fact, it sorts an array. That was an assembly implementation of bubble sort. Question? It's bubble sort. So it goes through each pair. If a pair is in a non-sorted way, it swaps them. And then it keeps going. And it keeps swapping and swapping and swapping until the array is fully sorted. Anyways, now that we're back, we will get right into our week 5 and 7 content. It's no longer hard. It's just a whole bunch of like theory bash. We have Otto taking over for the next 10 minutes while I have lunch.
Let's do this. Alright, so week 5 and week 7 to begin, we have the rights and responsibilities of the caller and callee in AAPCS. So AAPCS, just remember, this is just the fundamental functional rules that your assembly code should abide by. So if I accidentally go ahead and I change a certain register inside of a function I call an assembly, am I allowed to change certain values? Do I need to store certain values? Let's think about that. So what I'll do with this in mind is I'll just go ahead and turn on the document camera. Perfect. And get us to view the... Oh yeah, it might still be there. Yeah. Alright. Let's do this. Alright. So, let's run through the rights and responsibilities of the caller and callee in AAPCS. So, AAPCS, the way that we're going to structure our answer for this is we're just going to talk about caller, callee, the rights and responsibilities. Okay, lovely. So, now, just a little bit of info. We want to make sure that, okay, what are rights, what are responsibilities? Rights are, okay, I'm going to expect these things remain constant or expect that they change. And then responsibilities is what I'm doing the part in keeping a certain way. So, always easiest to consider responsibilities. Who's doing what? So, the caller, what does it do? It's going to supply arguments. Fantastic. That's the main thing it's going to do. It's going to put the arguments in the right places. That's typically your A0 through to, I believe, A1 through to A4. Those are your 4 argument registers. If you need more, where are you going to chuck them? You're going to chuck them straight onto the stack. So, can push further arguments onto the stack. Fantastic. That's really all that the function that your, let's call it main, needs to concern itself with. Supply the arguments in the right place and then let the function deal with it. So then what does the function do? It is expected to go ahead and save and restore certain values. These are, most particularly your program counter. It needs saving plus restoring, just for the sake of when you're going to be, it's your return point, okay? Your return point needs to be saved and restored every time you enter a function, right? So you save your previous return point and then you load back so that you can return to main, and main can tell wherever it's going, especially when you have nested functions. All right, what else do we need to do? Well, we just mentioned before that we can push further arguments onto the stack, so the callee has the responsibility to take them off of the stack. So taking other arguments off the stack. All right. Is there anything else the function really needs to concern itself with? Any guesses? Shoot. Potential for local variables? Or not quite. No, actually. Actually, sorry, my bad. Yes, those are the other ones that need to be saved and restored, because those are the ones that our caller function expect to be remaining the same. So yes, saving, reserved, saving the reserved registers. Do they need to be saved, or is it just good code to do so? That is true.
Unless you're like passing in by reference.
What if my code doesn't use those variables?
Oh, then if not, then
Exactly. So I guess depending on the scope of your callee, we'll have to save certain reserved registers. Sometimes it might be considered good code to just do so anyways, so you have more space to room with, more room to play with. Whoops. But yeah. And then I guess the most important part of calling a function, you have to know where to return it. So it has to return the function output in the R0 register, or rather, is it A1? Yeah. Returns the output in A1. Fantastic. All right. That's responsibilities. Now the rights. Pretty much the rights are what you expect to be maintained, right? What you're considering. So you'll find that they're pretty much a chuck back from each other on the most part. So you can imagine the caller, let's call it main, it expects my reserved registers to remain reserved, right? So that it can use them for other things. So reserved registers don't change. That's our main right. And I mean, we also have the other expectation that our output will be returned in R0. All right. We could talk about expecting my program counter to remain the same. Sorry, not my program counter, my return call address to remain the same. Yeah, all right. Now let's look at the callee responsibilities. Does the callee have any responsibilities here? Let's look at what we said before. Sorry, any rights. The caller has the responsibilities of supplying arguments and then pushing arguments onto the stack. It's all about arguments. Does the callee have any rights? I mean, technically, not really. We could just say that, okay, the callee has the right to say that, okay, I expect my arguments to be here. I expect there to be that many arguments. So, general, I need this many arguments. That's an expectation. But really, there's not much else. All right, that is AAPCS. Anyone have any questions? All right, we love 1521. So let's go ahead, just jump back onto the slideshow. That is rights and responsibilities. Next up, we have the read, modify, write cycle. Now, we want to give a clear explanation of when such a cycle should be used. So, read, modify, write. What does it, why do we do that? Does anyone have any ideas? So, something you might have found, particularly in your LED lab, is when you're changing LED lab and your touch lab. When you're writing to certain instructions inside of ARM, if you adjust, let's say, the LED red and then the LED blue and then the LED green, if you look very closely, you'll see, okay, it turns on red, the blue gets added, so it turns on purple, and then your green gets added, and you get white. It happens sequentially. So every change that you make is updated at that point in time that you change it. So something you might need to do with the read, modify, write cycle is you might only want it to change once. So you want to be careful about, okay, well, let's say I'm going ahead and I'm setting up my ADC. If I'm setting up my ADC, I want to make sure that I'm not accidentally putting in the wrong instruction. So I want to write my full instruction to the ADC all at once, and then it can go ahead and do what it wants. So it's a very important thing where we have to consider, I guess, the certain importances of other parts of the code. So something that I might go ahead and put down is, I reckon I might draw. Let's go back to writing.
You can type in VS Code if you want.
I could type in VS Code. That is a good point. Okay, let's do that. So let's go ahead and chat about read, modify, write. So the explanation for when such a cycle would be used, we mentioned if I need some kind of word, some kind of address in memory, and it needs to change in a certain way, and that gives me certain outputs, I need to be pretty careful. So if I want to go ahead and change this to OX1XX2, the X's being kind of I don't care whatever's in there, then okay, I could go ahead. What this is really saying is I need to change this binary wise into 0001. I don't care about the next 4 bits. I don't care about the next 4 bits after that. And then I need a 0010. Now you could do this by sequentially going and saying, okay, let's say I had this as some kind of R declaration, something I might do, and C-wise implement it as, all right, let's say R equals the value, which we don't know anything about just yet. So I'll just put down 16 X's. We don't know anything about it. I want it to end up being this. So let's go ahead. This is in ARM, so I should be able to go like that as a comment. Okay, I want it to become this. I might go ahead and OR for my ones and for my zeros. If I go ahead and I do that, I end up with what gives me the answer. So I'd go OR gets binary 0001 0010. That would set up my 2 ones that are in my desired output, and I could R and equal for my zeros. So how would I do this? I want to simply put zeros where I need zeros. The rest of them will be ones to preserve. Now, as discussed previously, this has a couple issues. The primary one being, actually I think I did that wrong, 0010, that's more like it. The main issue being that, okay, in this first modification, I've only changed these first two ones. Everything else could have been what other settings were setting up. This intermediary change makes it so that I get certain unexpected outcomes, whether it be only for a small fraction of the operation. So that is the importance of the read, modify, write cycle. So what is required is, rather than read and then modifying and writing and then modifying and writing, we want one clean bit of read it, modify it, write it. So I might go ahead and store it within some value called val, another register per se, modify my val register, and then rewrite it back to R. I should put this the other way around. In AC sense. All right, fantastic stuff. All right, and then now we have a nice question where we're considering finding stuff on the ARM. So consider the GPIO port 0 on the LPC 2478 processor and the below assembly code. All right, so they give us the certain offsets for the directions, the pins, the set and clear registers, as well as just the base address. All right, there are 4 LEDs on the pins 0.1, 0.4, and 0.1 through to 0.4, and there are 2 push button pins on 0.10 and 0.11. We need to write assembly code to set the directions of the 6 pins such that LEDs 1 to 3 are on and LEDs 2 to 4 are off. So, 1 and 4 are off. 1 and 3 are on. My bad. All right, let's go ahead and flip it back over to the, ooh, that was interesting. I might just jump onto VS Code, check this side on, so we can remain seeing this question. All right. Can probably do that. All right. So let's copy question. That's a good idea. All right. Let's do this. So first things first, we know the location of our base address. So let's just load that into a certain address that we're working. Typically LDR R0, and I need to chuck in FIO base. Oops, base. All right. I have the base address. Now I need to go ahead and I need to set the directions of the pins to input. Typically they are immediately set to input. All of them default to input on startup as opposed to being defaulting to output. So I might not need to change them just yet. Now recall, do I need to do anything with these push buttons? It seems like I only need to consider that the LEDs need to be outputs, push buttons are inputs. I don't need to really directly change the directions for them immediately, but we might just do that. So let's go ahead and do this. So first things first, I need the current directions. So I'm going to read, then modify, and write. So how do we get my directions? I'm going to load again the info at the direction address. So I need to go ahead, R1, recall that the offset that we've identified for the directions is 0, so I can just load directly from my base. So R0, bam. That gives me the current directions. Nice. Now we're going to set some of these specifically to outputs. That is pins 1, 2, 3, and 4. These need to be outputs, so let's go ahead and consider where they are. Recall, this is not starting at 0.0, starting at 0.1. So we need the first left shifted up to the fourth left shifted. So if we were to consider this just in full binary, actually let's just put it in, we end up with 4 ones and then a 0. This is what we need. The ones are indicative of outputs, so we need to add ones to this location. So what we're going to do is, the main modification we really need is setting just these LEDs to outputs, which means the last 5 bits need to be replaced as such. So one way we can do this is by going ahead and performing an OR operation of R1, which has our present addresses, present directions, and we're going to OR it with OX1E. So E is just binary for 14, and that gives us that. Okay. Now, is this all good? Don't forget numbers. Still need the hashtag. So, setting LEDs as out. All right. Fantastic. Now, is there anything else we need to do? Well, let's think about this. We have the pin offset. Okay. Set and clear. But we might want to be a little bit more. Actually, give me just a sec. We could go ahead and just double check that all of the buttons are set to inputs. By setting buttons to inputs, what is the easiest way to do that? That might be handy. We have this function called BIC, BIC. Now, BIC, it's like the AND method that I used. However, it just does the opposite. So previously, when we saw AND, I could go AND OX FFF0, and it would just turn this last byte. Actually, if I just went R1 and then OX FFF0, it would just turn this last byte into zeros. By using BIC, I can go ahead and instead only reference these 3 Fs and keep them as 1s. Okay? So BIC pretty much just does the opposite by setting to 0. And can set to, sorry, BIC
Bit
sets,
stands for bit clear.
yeah,
It
bit
clears
clear,
those bits.
clears those bits. Yeah. All right. So the equivalent, I'm going to keep this here. The equivalent of this is by using BIC R1 0x000 F. So here we are specifically clearing this last byte. So by using BIC, we can go R1. We want to ensure that the button on 10 and 11 are set to inputs. So let's go ahead and consider that. We'd need 10th and 11th. One way we could do this is if we were to take 3 and then LSL however many times, probably 10. Sure, we could do that. That gives us the 10th and 11th bits. But, I mean, we could be a little less savvy and say, okay, 10th and 11th, that's in the 3rd byte, and it's the 2 most significant bits. So what's better than 8 plus 4? It's C, so OXC, followed by 2 zeros. Really, it does the same, but I'll just say, or can use # hash 3 LSL hash 10. Either works, but pretty straightforward. So we've modified it. We need to write back. So we're going to store back in R0 the value of R1. So take R1, chuck it in R0. Writing back. There we go. That's inputs and directions of inputs and outputs set for all of our things. So we've set directions for all 6 pins, although technically, if you were in lab, you wouldn't really need to consider your push buttons just because they default to inputs on startup. So we did that, fantastic. Let's look at the rest. We need to turn LEDs 1 and 3 on, LEDs 2 and 4 off. Now there's 2 ways we could do this. Personally, I think the safer way is to just look at set and clear. Now we're not too worried about the just the immediacy of all of this happening at once. We just want it happening at the very end. So we can make this a little bit messy. So what I'll do, I'll just chuck that off. We're going to set LEDs 1 and 3 on, and then clear LEDs 2 and 4. All right, let's do this. So for set, what do we need? We need to add the offset. So we go ahead and we need to LDR. We could chuck it in R1 again, really, but doesn't matter too much. Chuck it in R2, and what we're going to do this time is, let's think about this. We could save the bit mask, yeah.
So we're going to set the 1 and 3 on, so that would be binary.
That's a good
10,
point.
10.
Do we need to read it?
No.
We don't need to read it. We don't need to read it at all, because set and clear, it's safe enough that we can only touch what we want to touch. And there's no punishments for doing anything out of order, because there's no such thing. So what we can do is we can go ahead, load a mask.
So as a quick reminder, especially online, the FIO pin field stores the actual values of all the pins right now. So you have to use the full read modify write cycle to read in the value, set the ones that you want, and then write it back. However, the set and clear pin specifically, you can just write to the ones that you want and ignore the rest. All it will do is it will set the value of the ones that you set to 1, or clear the ones that you set to 1 if you write to that particular address.
Nice. So we're just saying R2 is going to be equal to the binary value of 1010. So do you reckon we could do this with MOV, or is LDR more accurate for literals?
We'll talk about pseudo instructions very shortly.
Fair enough. All right. Now we're going to store this same value back into our set. So what do we need? We need to get our base address, which is still stored in R0. And we're just going to add on the offset, which if we look up, FIO 0 set offset. Fantastic. So this chucks LED high into pins 3 and 1, as we can see from the locations of the bit mask. And we can do the exact same thing for the clears. All right, LDR 3 this time, sure. Let's go ahead, load in the literal given by OX. Let's think about the pin numbers. Pin numbers 2 and 4. So when we do 2 and 4, we're going to need 2 bytes of info. So, I mean, we could just go for fewer bits, but what we need is the 5th one and the 3rd one. So just recall, these 4 bits are our bits of interest, This time we need to use a 2-byte word, or, I mean, do you reckon we could just do 5 bits? I reckon
No,
5 bits
so,
might. Yeah.
In normal ARM assembly, you can just use binary. However, in your particular program that you use, Keel, you must use only hex values.
Yeah.
So you just have to give that as OX14.
Yeah. So we convert this back x14, which will give us the same value. All right. And not to forget, we need to store it back R3 into this. Don't forget the offset. Yeah, I mean, something to note, we still have these hashtags surrounding our offset values. That is something to note. And that is that. All right.
Cool.
Very cool.
Thank you.
Let's jump back to Sudarshan.
Thanks for the lunch break.
All good.
Question.
Mm-hmm.
Yeah, so it's very clear how setting clear works. But why do we not have to clear all the bits and set clear right after all the items? Why wouldn't we just keep setting the bits that we have as one?
So why do we not need to flush it?
Yeah,
Right.
flush it. Actually,
So when it notices a change in the thing, it will take it and it'll do it and it'll just wipe it again. It'll wipe it. So because of that, there is a small time delay gap between setting it and it actually being set, which is why in the labs it said that if you set a value, you should wait for about 2 or 3 instructions for it to actually register before you can read from the pin value. So there's a small time delay, but that is expected with all of our little like extra things that we deal with. Cool. We're back to next up, the stack. All right. I love it's back. Cool. I love referring to the stack as a true toy stack. So we can see that the stack is a structure where you keep adding things on top, just like that little toy you had when you were 3 years old, where you keep adding rings on top of each other. You can only access the topmost item in the stack. You cannot go and fetch some arbitrary value in the stack. All right? There are 2 operations we have. We have a push instruction, which adds stuff onto our stack, and a pop instruction, which takes it off our stack. So now our question is, how do we store this in memory? I've already drawn it ahead. Cool. So we have our stack, we have a bottom of the stack, we have a top of the stack. We keep adding values. If we say at the bottom of our stack, let's say that's address 0. We add another value into address 1. Add something else into address number 2. We just keep adding like that. That makes sense. And then what we can do is we can keep track of the topmost value so that we can read that, or we can pop it, we can subtract, etc., etc. So if we draw it out, this is fairly intuitive, right? The bottom of the stack is at 0. If we add another value, let's say we push 1, there's a 1 here. If we push a 2, we get a 2 here. It's in the next address. If we push 3C, that's in our next address. And we just keep track of the top, right? We add to the top address as we push. But what if, for really no good reason at all, we went the other way? For no good reason, almost every processor nowadays uses something called a descending stack. It starts at the largest value, which is like FFFF, and it decreases as you add stuff to the stack, right? It adds stuff to a lower value. So the top of the stack is actually lower than the bottom of the stack, right? This is called a descending stack. The historical reason for this, if you flash back to 1511, we have a heap and a stack. A heap stores your current memories, a stack is your dynamic memory. The heap used to grow upward, and they decided that, all right, well, the stack can grow downwards then, so that we have most space. So that's the historic reason. However, yeah, so we have our stack, we have the top of the stack, keeps track of the last item that was added. But also, should we keep track of the last item in the stack, or should we keep track of where to store the next item? So that's the next empty available spot, right? So you can keep track of the top here, which is the value, or you could keep track of the top being the next empty spot. So this comes down to which operation are you doing more, right? If you're pushing, then you want to write to the next empty value, which if you're, let's say, writing. If you're reading more, if you're popping more, you want to read from the last full value. So that's the reasoning behind both types of stacks. In ARM AAPCS convention, we use a full descending stack, which means that it's a descending stack like this, and we refer to the last full element being the top of our stack. With that in mind, you have a question which asks, sketch the stack frame for a situation where the program calls function A with 7 arguments, the system has an empty descending stack, not a full descending stack, and the function A uses registers R0 to R7. If I tab out to the document camera, right, cool. So we said that 7 arguments. Am I on camera? Yep. We have 7 arguments. We have an empty descending, and we have the fact that function A just uses registers R0 to R7. 7 arguments to function A, and then function A itself uses R0 to R7, right? So let's draw up our vague like stack, right? We said that this is our high value, this is our low value, right? If we have 7 arguments, if we flash back to our AAPCS convention, we say that the first 4 arguments get thrown in our registers, R0 through to R3, and the remaining 3 arguments get put on the stack, right? So that means we'd be storing arguments 5, 6, and 7 onto our stack. The order of this, I don't think they'll particularly be fussed. If you, like, you could say arg7, arg6, arg5, or you could have 5, 6, and 7 in that order, right? I don't think they'll be concerned too much, but I am 95% sure if you look at our little Indian convention, we will go 7, 6, and 5 in this order. So now, when we call our function, so the main function sets these arguments on the stack. That means our stack pointer, our stack pointer is here. We're using an empty descending stack, right? So our stack pointer points to the next empty available slot. This is our main function, and then we call our new function A with this stack pointer. Function A itself uses registers R0 through to R7. If you think back to the convention, you're not allowed to modify the registers greater than R4, right? So you must also save those values before you mess around with them. So our function A would read these arguments in some fashion, and it would also have to save these R4, 5, 6, and 7 before modifying with it. So then we'd be like R4, R5, R6, R7, right? And therefore our new stack pointer at the very end is here. Our function A, what it would do is it would use these arguments. It would also, so it should probably pop these arguments off first, because you can't access a random point in the stack, right? So you'd probably pop these off first, then you'd save these to the stack. So this is our main stack, and then this is our function A stack. Cool? Awesome. Week 10 content, the compiler. Briefly explain the terms ARM instruction, assembler directive, and pseudo instruction with an example each. ARM instruction, straightforward. It's like your add, your subtract, your multiply, etc., right? It's an actual CPU instruction that gets executed by your processor. Let me. Cool. Briefly explain the terms ARM instruction. ARM instruction, actual CPU instruction executed by processor, e.g. add R0, R1, R2. No comma here. Right, this is our ARM instruction. Then we have a pseudo instruction. What's a pseudo instruction?
Multiple ARM instructions in just one line.
Pretty much. So it's, we call it syntactic sugar, or something that makes your life easy and can be converted into a very easy set of ARM instructions for the processor to read. So by itself, it's not a real instruction, but it gets converted down to a series, one or more instructions that the ARM processor can read directly. For example, syntactic sugar that gets compiled down to real instructions. Syntactic. Cool. For example, we have the LDR instruction. So now the LDR instruction is a bit funny because there's a real LDR instruction and there's a pseudo LDR instruction. The real LDR instruction is going to be like R0 and then like #1, right? That's valid. That's a real LDR instruction. You also have like, you can load from the address of, right? Like it was this with the offset. This is also a real LDR instruction. We also have a fake LDR instruction. Well, you can give an equal sign and then you can give it like some arbitrary number, right? What that will do is it'll get R0, it would load that arbitrary number into your R0. Now this is a pseudo instruction. I believe the next question deals with the exact specifics, but LDR, anything with an equal sign signifies your pseudo instruction. If there is no equal sign, it's your real instruction. If we flash back to the data sheet, I'm not sure if it makes that distinction. Let's see. There we go. You have the normal LDRs, which refer to registers and like an immediate value, which is what these stand for. They're explained down here, AM2. So these are your addressing modes. So those are real LDR instructions. And then your pseudo LDR instructions are the ones that have a label, where you know how you can like give arbitrary labels to pieces of data, like your DCD. You can load a label, which is a pseudo instruction, or anything with an equal sign is a pseudo instruction of LDR. Cool, cool. 0x. Cool. And then finally we have our assembler directive. The assembler directive is, well, as it's in the name, a directive to your assembler. Your assembler is basically your compiler of your code. It takes your assembly code and converts it down to the series of literal ones and zeros in correct or accordingness with this method, right? So your assembler directive, sometimes you might want to give it like some bit of extra help to tell it, I want you to like compile my code in this particular way. For example, the DCD that we use to declare stuff in our array is an assembler directive. It's not a real piece of, it's not a real instruction, right? So DCD tells the assembler, hey, take this value and store that directly in memory. This is not a real instruction. I just want this information to be stored here. Another assembler directive is your labels that you can give. If you, I wonder how far back I can undo. Let's see how long this runs for. We might be here a while. Oops. There we go. We had our whole jump table, right? We have this jump table is a label. This is a directive to our assembler. The word jump table itself does not actually get compiled down to anything. But however, when we do like LDR, we say like save into R1 jump table, right? This is a assembler directive, this will go, the assembler will be like, all right, this DCD is actually at memory address number 9. So I will go here and replace it with 9, and then I would get rid of this. So this is what your code actually compiles down to. So that's an assembler directive. Cool, I think that's it. Yep, and an example each. We just talked about labels. That's an example. Next up, below is a set of loading pseudo instructions. Rewrite these instructions in a single instruction if possible. Otherwise, explain the equivalent machine code. So we have LDR. I wonder, there we go. Am I able to copy the text out of here? Nope. All right. We have LDR R0, FF 00000, LDR R0, R1, 0x, what was it? FF 00, FF 00, FF, and then we have LDR R2, 1, 2, 5, 7, 8, 0x, we. Right, these are our 3, there's a capital X there. These are our 3 LDR instructions, and we have a litorg down here. Litorg is an assembler directive, not a pseudo instruction, and then these 3 are our pseudo instructions. If we look at this value, this is a 1 bit, 2 bit, 3 bit, sorry, 1 byte, 2 byte, 3 byte, 4 byte. This is a 4 byte, 32-bit value. Our instruction itself is only 32 bits. So we cannot possibly have a 32-bit immediate value encoded in our instruction, right? If we look at the data format, there we go. Yeah. Load store instruction formats. We have like 10 bytes for the immediate. We don't have all 32 bytes because the rest of it's used for the actual instruction, right? So we need to do some clever magic if we're going to want these values stored as data. If we look at this, FF with all these zeros is the same as 0xFF left shifted by that's 4, 8, 32. Right? We can do this. You remember that we have like an LSL command, right? So we can rewrite this as move into R0, the literal 0xFF, and then we can, not 32, sorry, 24. That's 2, yes, 24. Take that, rotate it, LSL by 24. All right? This is a valid real instruction if we look at our mov command. Where's mov? There we go, mov. Right? We can mov into our destination register, shift op, and shift op, like we saw down here, was, good God. Ah. I can't find it, but yes, you can take an immediate value and you can shift it by a constant. So these work because this is an 8-bit value and this is a 5-bit value. So 24 is 0b. Sorry? Yeah, less than 32. This is allowed. I swear it tells you. There we go. So you can have an immediate of 8 bits shifted left by 5 bits. That's the limit that you can fit into our instruction because we only have that much space available. You can see here. There's a shift operand. Offset. There we go. The offset value and then a shift applied to it. So you only have those 13, 12 bits available. So this is valid. You can convert this pseudo instruction into this mov instruction, which is a real instruction, all as well. However, if we look at this, we can rewrite this as 0x that with another 2f's, except this time it's rotated to the right by 8 bits, right? Because these two fall off the edge and get shoved to that side instead. So it's rotated to the right by 8 bits. So this is that, ROR 8 bits, and that means we save these two zeros at the front. However, this is still 1, 2, 3, 4, 5, 6, 24 bits. That's too long. You can't do that. You cannot have 24-bit immediates.
Sorry, what is the maximum bits? Is it like the, so I see like INN12 and INN5. Does that represent how many?
Yes. So in this case, it's IM8, which is an 8-bit immediate shifted by 5 bits. So that's the limit we have. Mm-hmm. Exactly. So because of this, we have another command called MVN, move with not. All right? So it takes your immediate, it nots your immediate, and then it shifts it, which very perfectly does exactly what we wanted to do. So instead of taking that whole big number, what we actually want is so this, if we take the not of this, we get 0x 00ff 0000, right? And then this is the same as that shifted left by 1, 2, 3, 4, 16 bits, right? And this is, again, this is our 8-bit value. The number 16 is only 4 bits, so it fits perfectly within our constraint of 8-bit immediate shifted by 5. And so if we rewrite that, we have MVN into R1, we take 0xFF, we shift it we shift it left by 16. Cool beans. Finally, we come to OX 1, 2, 3, 4, 5, 6, 7, 8. Unfortunately, we cannot. This cannot be represented as an 8-bit immediate shifted by 5 bits because it has no real pattern to it. So unfortunately, we just have to like succumb to the pseudo instruction. What this will do is it will store it in memory, like it'll go and like DCD it, and then it would replace, like the assembler will go and DCD your that, and then it would actually just LDR PC -4, because your PC would be 2 ahead. You want to go back 1, you want to load that into memory. You'd do that, or actually, even without the -4, probably just do this, because you'd also have to have a branch. Because if you don't, so if you do this, where you LDR, like let's assume there's a NOP here for just for fun, we LDR the value into R2, it goes to the NOP, it does nothing, then it gets to the DCD. It doesn't know the difference between an instruction or just data. It will see a 32-bit value and it'll be like, all right, this is an instruction. I'm going to execute this instruction, except like, you don't know what that instruction means. It could be doing whatever the hell, like for what we know. Could be some instruction in this format. It'll go and do something random. So we also need to have a good branch here to just hop over this stuff. So we can do branch by 4. You have to hop over the DCD instruction. And then finally, the litorg means do all my DCD now. So to get over the fact that you have to branch over this, what you could instead do is you could have this, have all your extra program here, right? And then at the very end of your program, then you DCD. And then you'd give this a label. You'd be like, my data, give it a label, right? And then you would LDR with that label specifically, right? This would go and sort of load the value, sorry, not label, it would be my data here, my data. You would go and load that. That is fine. However, if your code is more than 32 megabytes, you cannot address that far, which is what the litorg does. Litorg says, save my data right here. Any like pseudo instructions, anything that you have to save, do it right now. So if I chuck a litorg here, what it would do is it would take your data, shove it here, and then have all the other instructions following it. Without the litorg, your code would finish and then data would be sent. Does that make sense?
Where do you place the little?
Wherever you want to have your data saved. So if for some reason, let's say I have like 5, 10 different instructions that all involve some weird constants, right? Like these are all some random constants, etc., etc., etc. Then if I chuck a litorg here, this is an assembler directive, the assembler will go and do all my DCDs right here. And then I can have like add, sub, mul, LSL, etc., like all the random stuff. If I don't have the litorg, it will go and DCD all your data at the very end, because that's like good practice, right? So the litorg is good if you have lots of code and you want to like break it up into sections. So you can say, have all my required data for this function right here. Cool. That's litorg for you. In the interest, maybe, no, I can go through this. All right. How does this look in memory? Assume little endian, right? So we have the data, we're DCDing some hex value, then we're DCBing two hex values, then we're giving an align command, and then we're giving another DCB and another DCB. Anyone know what align does? Mm-hmm. So if you couldn't hear that on the instruction, sorry, on the recording, what the align does is so if we look at DCB and DCD, DCD declares 4 bytes of information. So it saves the next 4 bytes right there. A DCB is only 1 byte, so it will save the next singular byte. This means that if I have 1, 2, 3, 4, 5, 6, 7, 8. Right. So my DCD will take up all of this. DCD. Right? Goes here. But my DCB only takes up this bit of space. Let's fill that a different color. If I then go and try to DCD again, take up the next 4 bytes. Right? It'll go and like DCD this. And before this, I had 4 bytes of instruction. Right? I had my instruction. Let's just say I had like a add instruction. Right? Let's pick a nice different color. Green. 11, 12, 13, 14, 15, 16, 17, 18. So I had an add instruction, then I had a DCD, then I had a DCB, I had another DCD, and now I have my next instruction. I have my merge this, I have another add instruction. Right? This is problematic because, as we discussed earlier, your program counter keeps track. Your instruction's 4 bytes. Right? So your program counter is looking for 4 byte chunks. So your program counter says, all right, that's instruction 1. And then if I drag this down, there we go. This is instruction 2. This is instruction 3. This is instruction 4. It's offset. Do you see that? Instruction 4 is offset now because our DCB, a singular byte, ruined the alignment of our memory. So we need a way to get this back aligned so that instruction 4 actually reads the whole add. We need to basically shift cells down. Oh, not that much. We need to add some padding here so that instruction 4 looks in the right place. Right? We can't actually pad our program counter. So what we do is instead we'd add like 3 bits of wrong way. We'd instead do, because we can't do that, instruction 4 and 5 read in the right place. What we actually need to do is just move, take this, we need to move the add instruction down here. We need to like waste this space. right? We need to pad it so that it actually reads the instruction aligned properly. This is what our align command is for. Align 4 says that it aligns, or if you have any data that's unaligned, it aligns it to the next 4-byte boundary. If you have an align 7, it would align it to the next 7-byte boundary for some particular reason. If you have an align 4, 3, I don't think there's really any good use for this ever. However, it's an assembler directive and it's in your lecture slides, so you should know it. Align 4, 3 does an alignment of 4 with an offset of 3. So it takes every 4th byte and then offsets by 3 and then it aligns the data to that. So yay for no reason. Okay, if we draw this out now, are we back? We are back. Cool. Let's say I'm just going to draw a nice good table again. 4,000, 4001, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C. Right, this is my data table. This is the information. I might have to figure out how to have this show up. There we go. Cool. If you're online, just like pause it or like copy the code out somewhere else. Oh wait, have I been showing the document camera this whole time? Maybe. Whoops. How much did we lose? We lost the loading LDR stuff, alright? Well, you have my voice, you can try and like reconstruct it. I'll release written solutions later. Sorry? 22 minutes. Yay. That's alright. I'll release like full worked out slides later. You can watch along. So if we have this data and we DCD, what is it? 00008315, and the code said assume little endian, we just do the stuff in reverse as we said. So we'd put a 15 here, we'd put an A3 here, we'd put a 00 and a 00. Right, this is our DCD. And then if we do a DCB, what this would do is it would go and put in our OX22. This is our DCB. And another DCB for OX44. And then we hit our align statement, right? We have an align for 3. This takes every multiple of 4, offsets it by 3, which means that normally our alignment would be 0, 4, 8, and C. If we offset it by 3, that means we hit 3, 7, B, etc. The next available spot that fits the alignment is 7. So what it would go and do is waste this bit of space, and then the next stuff that we add, we have a DCB of OX72. It would chuck our OX72 right here, and then our OX11 here. Right? So that's our align statement at work, and then this is our next DCB. This is our DCB after that. Cool. I'll remember to turn the document camera off this time. Cool, I'm back. I will also, there we go. This is a quick short review of the LDR pseudo instructions. Cool. Next up, processor modes. This is a bit of content in week 9 that they can't actually make you do too much about it other than ask you what the 7 processor modes are. What are the 7 processor modes in ARM? You don't need to memorize them because they're on the formula sheet. Right down here. Our program status modes, we have a user, fast interrupt, interrupt, supervisor, abort, undefined, and system. Those are 7 modes. Yay, take 3 marks and move on. We also mainly write programs for the user mode because we're a user. The other modes are for doing other weird fun stuff. They did once ask how you can use the undefined processor mode to implement custom instructions. I will not go through it right now in the interest of time, and also because it's like extension content. However, if you want a little bit of fun fact, take a photo of this, or just like quick skim through. This is how the undefined processor mode works. I'll wait for like 20 seconds and then move on. Good fun. Additional details. Cool. Compiler, we did this. Processor modes, yes. Final boss time. Alright, this is the final boss. This was my final question in my exam. They gave this ugly looking formula and they said write a program to implement the below formula in ARM. So your job is to write 2 pages of ARM assembly by hand in the final exam for 20 marks.